Good. Okay, well this is abstract algebras and where to find them. Magmas, monoids, and more. My name is Reid Evans. You can find me on Twitter at Reid and Evans if you would like. I work for a company called ResultStack, who was kind enough to allow me to travel out to Denver and enjoy this amazing weather and this conference, and basically pay me to come out here, which is pretty incredible. Before I start, I'd just like to say, let's give a hand for the conference, all of the attendees, the organizers, everything. Has everyone had a good time at the conference? Yeah. So I run. Actually, we had it was our first year this year, and back in Knoxville we had a one-day, one-track conference. Nowhere near as polished as anything that's happening here. So it's really, really impressive, all the stuff they've done. So let's look at kind of what our overview is going to be today. So we're going to start off, obviously, we've got to say, why should we care about abstract algebra as programmers? What about category theory? Because there's probably been a lot of talks that you've been to that talk about category theory things. And then we're going to say, what is abstract algebra? And that's going to be kind of a bottom-up or like bottom-up kind of thing. And then what we're going to do is we're going to go more of a top-down kind of approach to thinking about some of these things. So apologize for my accent. I am from Tennessee, so if you can't understand me, that's probably the reason. I did wear shoes today so that you all would not know that I was from Tennessee. I'm also not playing a banjo, so that makes it difficult for you to know where I'm from. So why abstract algebra? Why should we care about abstract algebra? So if I were to tell you that what I wanted you to do is to do something very, very creative with some blocks, and I give you the choice of the blocks on the left or the choice of the blocks on the right, which one would you probably choose? Like if you wanted to do something creative, to come up with new ideas that maybe someone hadn't even thought about doing when they created the blocks, would you choose the one on the left or the right? The right. So what we're actually saying here, we've got 26 blocks that fit together in exactly one way. And over here, any two blocks we can combine in 24 ways. And what's interesting is that the way that this thing balloons, I'm not even sure what kind of algorithm that it actually is, but if you have 6 blocks, it's 915 million different ways. So 26 of them is probably not computable, given our current technology, what you could actually do with it. So it's a way, in this case, that we're taking these blocks, and what we can do is we can say, we've defined this interface, this structure that we have. There are these ways that you can combine these things together in ways that the people who created Lego have no concept. They're doing things that people that created, the patent have no idea for. And so this is an amazing quote from Bartosz, who is obviously very, very well known for category theory. And he's talking about what we like to do in programming. We like to take big problems, break them down into very, very small problems, and then we want to compose those problems into bigger, to solve the bigger problems. That's like a lot of what we do, right? Which is very, very similar to my Lego analogy earlier. Said another way, we want to be able to define ways of composing small working pieces into larger working pieces, but it goes beyond that. Because what we would really like to do is to say, if we have one small thing here, and we have another that works, that is correct, and we have another small thing here that is also correct, if we combine the two, what we want to do is to say, this must be correct too. And if we can do that, then we can build up arbitrarily large systems that we know must be correct because they're combined of a whole bunch of small things that are correct. And that's why abstract algebra. So what about category theory? How does that fit in? Is it different? So here's my hand wavy slide. So abstract algebra, the portions of abstract algebra we're going to talk about today are going to have this sort of type signature. So you have one A, you have another A, and we get another A. Okay? Now with category theory, we've got a little bit more stuff happening here. We also get more power when we do that. But we have some more things happening here. So we've got a more complex signature for functor and monad here than we do for some sort of a binary operation, closed binary operation. Okay. So show of hands, who here writes in a language daily, gets paid to write in a language that has higher kind of types? Okay. Who here does not? Okay. For everyone in the room, if you work in a language that has higher kind of types and you are trying to explain some stuff to people who work in a language that don't, it's kind of difficult, right? That's why there's like 1,000 monad tutorials. And for those of you who don't work in a language with higher kind of types, all the code that I'm going to show today is written in TypeScript, which does not have higher kind of types. So you can do this if you have higher kind of types, this is great. You can still do this. If you don't, that's fine. You can still use these techniques. So you don't have to approximate something. So 4.4%, this is according to Stack Overflow's most recent survey. Now that's a bit self-defining given who typically goes to Stack Overflow. But 4.4% of respondents worked in a language with higher kind of types. It means most people don't. And so that's, I think, a big reason for why. So, you have a question? Oh, sorry. So if you can only approximate a concept in your language, you're only really going to have an approximate understanding of what the thing is. So I'm not saying category theory is a bad thing at all. It's amazing if you have higher kind of types and you can do some of those things. But from what I have found, there's people who've worked in functional languages for a very, very long time that don't have higher kind of types, that kind of only somewhat understand them. So that's kind of why. Okay, so what is abstract algebra? Well, it's the study of a set and the operations that act upon it. So this tells us that it's kind of based off of set theory. But that's a bit abstract of a definition, I think. So let's break this down. So it's a study of some type and the functions that act upon it. Okay, so that's a little bit more towards functional programming and what most of us are here for, right? And you're thinking, pretty sure that's what I do all the time, right? I have some types, write functions for them. How is abstract algebra different? What makes abstract algebra different from that? So, the main thing that I want you to take away from today, from this talk, is a focus on which properties are upheld by different things that we can do. So, if we have this equation, 1 plus 2 equals 3, what kind of properties can we tell immediately from just this one simple 1 plus 2 equals 3? What can we tell about numbers over addition with this? In this case, we can say that they're closed. So let me define closed. So sometimes that'll be called totality. It depends on what you're looking at. They're kind of defined differently, but it's a similar concept. So what that means is that it does not matter which two numbers you give me. If I add them, the result is always going to be a number. Okay, that seems really, really simple, but it's the basis for what we're talking about. It's what keeps us dealing with small, simple components. What we can also do is we can say that if we add 1 plus 2 together and then we add 3, we get the same thing if we add 2 and 3 together and then we add 1. And that's the associativity property. So we can group the terms however we want to. The order left to right has to stay the same for associativity. We also have this concept of an identity. So we can add 0 to anything and we get whatever that thing is. And then we have this cool thing. So if we add a negative x to any x, we get back the identity, which is invertibility. And then actually, as it turns out, numbers over addition are commutative. So we can actually switch the order. So these are some of the different properties that are going to define what types of algebraic structures that we actually have. And once again, this is all our bottom-up stuff. So this is kind of motivating what we're going to talk about, okay? So said another way, AA is like Monopoly. It's all about the properties, okay? That's what we need to focus on, is which properties are we upholding. I really like this little table, matrix. I don't know. Well, table, matrix sounds way too advanced for my knowledge. So what you see is across the top we have the properties. Across the on the on the y-axis here, what we have is the different types that we have, the different structures. So we've got a whole bunch of different algebraic structures, and what you can do is you could say, okay, well, so if what I have is some structure that's closed or has totality, and it's associative, then I've got a semigroup, so I can do any of the cool things that we can do with the semigroup, I can do with this type. And there's way more types. I have this line here, so you notice up above that in the top three, they're not closed. So you've got things like groupoid, category, semigroupoid. That's a little bit more like some of the stuff for obviously category theory. It's not closed, and that's one of the benefits of abstract algebra, and one of the detriments depending on what you're doing. So magmas, it's in the talk title, so I got to talk about magmas. Now I don't know about you all, but when I hear the word magma, I immediately think of this, and this is the first slide to show approximately how old I am. There will be more. That's what I think of every time. So what is a magma? All right, so it's a set with a binary operation that is closed. Now I've said these words before, but let's break down what those are. So a set, what we're really talking about is all possible values for a type. So with addition and numbers, what we said was any number, you can give me two of them, I can add them, and we'll get you another number. So a binary operation is just basically a function that accepts two arguments for what we want to talk about with it. And then closed, it must return a value of the same type. Okay, so that's what a magma is. And the function signature, if you wanted to do a function signature for it, it's this A goes to A goes to A. So you see it's the same type all the way across. It doesn't matter which type it is, because it's polymorphic, it's generic. But what matters is it's the same one going across, and that's the closure thing. So what are some examples? Well, as it turns out, we can use infix notation and do hello world. That works. 1 plus 2 equals 3. And you see the binary operation I have in yellow, and the set is defined in the green. We can do prefix notation. Really doesn't matter how we end up doing that. But the important part to remember is that this closure property, it keeps our code simple. And because I mentioned both of those, this guy appears every time to tell me that, yeah, he could have told me that was the case. But the reason that closure is going to keep our code simple is because, think about this. Is 3 any more complex than 1 or 2? Probably not. Is the string of hello world any more complex than the string hello or the string world? So we're combining these things together, and what ends up happening is that we get this larger description of what we want to do, but the individual parts are no more complex than the whole. So how are we going to code to a magma? As it turns out, no one really seems to do this. It's not very practical, and the reason that it's not very practical is because it doesn't uphold very many other properties or axioms. As it turns out, there are some things that we could do with just straight magma, but the thing is it really it provides the basis for all of the other structures that we're going to see, because it introduces this concept of closure. So the next structure that we're going to see are semigroups. And this one's really going to date me. So semigroups are not quite like this. I'm from the South, so anyone will tell you this is Van Hagar, not Van Halen. You always really wanted the group to work, and it was just never quite a full group. I know, they don't get any better. Not proud. So what are semigroups? So semigroups are basically magmas that are associative. Well, we saw associativity earlier. But so once again, it's a set with a binary operation. That's going to be common for all the stuff that we're talking about. But it's going to be closed and associative. So in this case, the order of operations does not matter. So as we talked about, we can first sum 1 and 2, or we can first sum 2 and 3. We still have 1 plus 2 plus 3, 1 plus 2 plus 3, and we get the same value. So this, once again, this is bottom up. We're going to see top down here in just a little while.
Shouldn't this be grouping of operations does not matter.
Yeah, fair enough. Yeah, this is the problem is, this does not mean that I could take, associativity does not mean that I could take 3 and throw it over here, and 1 and move it over here. I might get a different value. With addition, I'm not going to. But in, like, if this was subtraction, subtraction's not commutative, so it might have made for actually a better example. So here's where we're going to see a little bit of code. So what would this look like in code? So this is TypeScript. Does anyone here write TypeScript? Okay, cool. So it's got a very C-like look to it. But what we can do is we can define an interface. This would be a type class if you were in a Haskell or what does Scala call them? Traits? Is it trait? What is it in Scala? Trait. Okay. So we're going to append, and we have the same structure of an A goes to an A goes to an A. And then what we can do is we can define constants for like a sum semigroup, a string semigroup, whatever we want to. But you see that because we've defined that it's a semigroup of number, append will obviously have to take 2 numbers. And in the string case, append will take 2 string values. So this is very, very easy to define. You do need a language that will give you generics or type parameters. So this won't work in Go, but it will work in pretty much any other mainstream languages. If you're in a dynamic language, then you can do whatever you want to, and it'll still work. Hopefully. If you've coded the rest of it right. So what can we do with that? Well, one thing that we could do is we could define this concept of fold semigroup. Okay? So what we could do with the semigroup is we can say, give me any semigroup for an A, give me a starting value that's also an A, and then if you give me a list of A's, then I can actually perform a reduction over those. So I can start at my start value, and then I can pairwise combine all of the others as we go through. And so you see at the bottom, we get, if we were to fold the semigroup using the sum semigroup, if we start with 0, we sum the numbers 1, 2, 3, then we get 6. And then we can do hello, how are you? But we've written a generic way now of being able to abstract over any semigroup that we can define. Does that make sense? Any questions on this?
This is all JavaScript?
This is TypeScript. Yeah. But so, kind of. TypeScript plus plus, or JavaScript plus plus. Yeah. That's I don't want to think Microsoft would be happy with me saying that. So, what is associativity bias? Because realistically, where I said that with the Magma approach, it wasn't very practical, technically we could have written that had we based everything off of a Magma. Now, what associativity can bias is, think about this. If we can group the terms however we want, then what we could do, see, as we're grouping, we can group 1 plus 2 first, or we can group 2 plus 3 first. If we have all of these different, let's say these green circles are elements that are lined up. These are elements in a list that we're going to have. What we can actually do is we can group them and run all those in parallel. So for some simple parallelization kind of things that we want to do, we could actually parallelize those. So we could run all 4 of those at the same time to get 4 back. We could parallelize the next 2, and then we could return the other 1. So some pretty neat optimizations that we could do. Obviously, I didn't write that in my fold semigroup that I wrote, but these are some of the things that we could do now that we have associativity. So the next structure that I want to talk about are monoids, because they're basically a semigroup with an identity added to it. I mean, these are really, really cool structures. Yeah, they're really cool structures. So they're going to be another set with a binary operation, but they're going to be closed, associative, and they're going to have an identity. So an identity is just a value that we can be appended to another value that will not change the other value, which looks way better if I just write it in some pseudocode and you all can see it there, right? So 0 plus n is going to equal n, which is also going to equal n plus 0. So it doesn't matter. In this case, the identity is commutative. So the identity value can be thrown on the left or the right of anything, and it still works. Yeah, so most semigroups have an identity. There's a very popular talk where someone suggests another way for always having an identity for it, and they get called out for it. So I will not make that same mistake. But anyway, I digress. So we can see that it forms this kind of a hierarchical thing in the way that we implement it. So what we do is we say, we have this interface called monoid, and it's going to extend this semigroup. This kind of means inherits, implements, not implements, I guess it's inherits, or depending on what kind of language that you want. And Haskell, well, actually Haskell does now have semigroup and the monoid thing. PureScript does the same thing, where monoid just extends semigroup and adds the additional property. So what we can actually do then is we can take our sum semigroup that we had earlier and then just add the empty clause to it. So we're kind of reusing code. What's neat is that if we define it this way, then we can still use our fold semigroup because it is also a semigroup. It just so happens to also be a monoid. And we can now define this concept of fold, because now what we didn't have before with our fold semigroup is we had to say, okay, give me a starting value, because I don't know which instance or which value you want to start with. But now we do, because our monoid satisfies everything that we need to fold. It abstracts all of that into a singular structure that we can then fold over. One thing that you'll notice is that if you've seen like foldable from Haskell, is that I'm doing this specifically to array. You can actually write this in the other where you could do some sort of a foldable. That's very, very easy to do also, but I just didn't want to confuse anything on that. And so what you see is that if you have a sum monoid, then you can just pass an array of integers to it, and we get the value out. And the same thing if we have our string monoid, then we can reduce it. So it's this concept of, now that we have an identity, we can sum up 0 to many things just by passing it to this fold. Does that make sense? So this is all neat. We've got primitive types. Like, who here gets paid a whole lot of money to like add and concat strings together all day? Nice. We'll chat later. All right. So the thing is, right, is we work with more stuff than that, right? So what if we have this person interface? So this is just like a record. It's got a first name, last name, and an age, and then we have people here. So this is me. And then my son, and I actually had to rewrite this. He just turned 6 on Friday. So what if we wanted to get the total age of all of the people in this list? What structure would we want to create for that? A monoid would be great, right? Because we may have no people in the list. If we had a semigroup, we'd have to start with some sort of person. So it's easy. We'll just write our monoid instance, right? For our person. I think it's kind of difficult. What do we do with first name if it's empty? Like, age makes sense, because really what we're talking about doing is summing up the age. But then, how do we combine first name and last name? And I guess we could concat them together, but it doesn't work that well, right? Like, so what are we going to do? There are ways that you can do it, but all of them just seem kind of hacky. So what we can actually do then is we can define this concept called foldMap. Who has heard of foldMap? Who has used foldMap? Right? Crazy useful, right? Yeah. You can foldMap all the things. Well, not all the things, most of the things. But so what's interesting, if you look at the type signature, it really tells you what we're going to do. So if you give me a monoid, so something that knows how to combine 0 or many a's, and you give me a function from some b to that a and a list of b's, then I can produce you an a. And so the only real difference between foldMap and fold is this little bit right here, where we take, as we're reducing through, we take whatever our b is and we apply this function to it first to transform our b into an a so that our monoid instance can work on it. And if you've seen if you've heard of contravariant functors, this is very, very similar to a contravariant type of functor. Because what we're doing is we're saying we're going to transform the input that we have into something else so that we can continue going forward. And so then what we can do is obviously we can run this through and we can say, all right, so for our function here is going to be our lambda, so x, and then we'll just get the age property of the person. And then we'll pull it out. We could write fold in terms of foldMap if instead of passing our function here, we could just pass the identity function and then we would actually have fold in terms of foldMap. Wouldn't be quite as efficient, but we could do that. So what I like about this is now we're taking small little primitive pieces of data, of types of values, and we're going to use our foldMap that we can basically create for free. We're going to take these small little pieces and we can now start working on bigger and bigger structures from just some small primitives that could be defined anywhere that we wanted to. So we're getting a whole lot of code reuse out of this. So another really, really neat one, we're skipping quite a few here. We're adding a couple properties here, is this thing called a join semilattice. And so it's got 4 different properties that it needs to have. It's going to be closed, associative, commutative, and idempotent. And so what's neat about all of those things is that if we're commutative, that means we can swap the order of arguments. So if you're thinking about parallel computation, if we can swap the order of arguments, then that means we could go off, make a bunch of network calls, have a whole bunch of stuff come in. We don't care which order they come in, because we can apply them in any different way of things coming in. So it doesn't really matter the order of the operations coming in. So our trivial example is 1 plus 2 is going to equal 2 plus 1. But if we thought about those being over some sort of a network call or I/O or anything like that, it doesn't matter which order they come back. We can just send them all out. Whenever they come back in, we're good. But that paired with idempotence actually ends up being really neat, because idempotence says that performing the operation multiple times does not change the outcome. So we only get the result, it only makes a difference the first time. And here's an example in code, is if we were to take the absolute value of -1, it's the same thing as taking the absolute value of the absolute value of -1. So what that means is that not only does it not matter the order of these things that come back to us, it actually doesn't even matter how many times we get the same message, because we're only going to process it one time. That's really, really neat. So if you've heard of like CRDTs or these eventual consistency kind of things, this is one way to do that kind of a thing, is to realize that you have this semilattice structure. Okay. So there's all of our bottom up. We've defined some of the structures. Now, how do you know if you have one of these structures? That's what we're going to talk about. Any questions before I go on with this? Yes?
I was a little confused about the idempotent.
Yes, absolutely.
Operation, how you, like math apps is
Yeah, it's just a single one.
operation.
Yeah.
I'm confused about idempotence and binary operation.
Yeah. So you would still have it. So another one that would be, well, I'm giving away a slide later, but if you were to take the maximum of 2 values, so if you take the maximum of 1 and 2, and then you take the maximum again of 1 and 2, it's still the same. It's still 2. It's always going to be 2 as you go forward. It breaks down just a little bit because of that, but yeah. So where can we find them? Oh, those were supposed to come in later. Okay, so so what about ordering? So is it closed? So if we're thinking about if our business domain that we have is what we need to do is we need to develop some sort of an ordering system or some way to define what it means to order a bunch of things. What we end up having is it closed? Well, we can take some predicate or some ordering that is someone's last name, and then we can take another one that is someone's first name. We can smush them together, and then we still have this ordering, this order by, if we're using SQL, order by last name then first name, and so we still have an ordering. It's a more complex ordering, but it's still just an ordering. Does that make sense? It's also associative because we can say last name, then first name, then age, or we could actually say first name, then age. We could group first name, then age, or we can group last name, then first name first. It really doesn't matter either way. We also would have an identity, which we could also define, especially with like the Haskell ORD type class that we could have, where we could just say, I don't care what two things you give me, they're just equal by default. And that would basically be our identity in that kind of case. And then it's also idempotent because we can continue ordering by last name as many times as we want to, and it's not going to have any additional effect after the first time. But it's not commutative. So what does all this mean? Well, it means that if you're dealing with something, if you're dealing with ordering, you don't have to worry about doing a whole lot of checking that this thing doesn't happen. That's an optimization that you could add to it. But in that domain itself, that domain lends itself to having these properties. And so what that means is that it's some sort of, it's closed associative identity, which means, okay, well, we know we've got a monoid because those are the properties that a monoid upholds. And it's also idempotent. It's not commutative, but it's idempotent too. So the whole concept, though, is looking at our domain, our business domain that we have, not our mathematical domain, but our business domain, and then trying to determine which properties are upheld for it. Does that make sense, how we went about that? Going through a list of some of the mathematical properties, and I've just shown a very small amount of mathematical properties here that we can go through. But if we start with that, then it really informs the things that we can do and the things that we can trust about. So what about regex? Who here has worked with regex before? Who here only works with regex immediately after they've forgotten how to regex? The same hands? Okay, yeah, that's me every single time. So what about regex? Is regex closed? Can we take two regexes and produce another regex? Yeah, if we treat them as strings, we could do that. Now that doesn't mean that we're going to get a valid regex for any two strings, but yeah, we could do that. What about associative? Is it associative? I think so. We could do that. What about identity? What could we do for our identity? So if we were thinking about modeling regex, what we wanted to do is we wanted to say, I have some regex, and I want to be able to append another regex to it such that it doesn't change anything, and I could append that, whatever that is, to the front or to the back. Does anyone have any ideas what we could use?
S.
Yeah, dot star would work. S would work. In my case, I kind of copped out. I just used empty string, but all good solutions. Yeah. So if we're going to treat it like that, we can, we just say empty string. Yeah, there's lots of different things that you could do. But these are the kind of things that you can be thinking about for what do I have? What is this thing that I'm modeling? Is there an abstract algebraic structure that I could use so that I could inform some of the things I could do? So yeah, we could do that. What about commutative? Does commutative work? No. No, commutative for sure does not work. Well, you could do it. It's going to be a completely different answer, which is why it does not work, if you were to go that way. CSS select. Oh, yeah, question.
So you mentioned earlier, so I was talking about combining regexes. And
Yeah.
if we are only looking at these as plain strings, then a lot of these rules apply. But if there is a valid regex that when combined with another valid regex produces an invalid regex, that seems like it would break some of these rules.
Mm-hmm.
And how would you model that?
Right. Yeah. So that is very true. That would be something that you would want to model. You would want to handle in whatever structure you create to model regex. You could handle that.
So a simple function that would take two regexes and combine them could model that as returning a maybe or an either, for example. But if we were trying to create, use one of these higher level concepts, it seems like the return type being impacted by changing from regex to an either regex or maybe regex.
You lose closure in that way. Yep, you're very right. You would lose closure in that way.
You
Yep.
could use something like dependent typing to basically model like an AST for regex, and then you can't, like, it won't compile if you try and add two regexes together to form an invalid regex. It's like you can model it in such a way that your domain is the set of valid regex.
So you're not saying to just model a type that is regex. You're saying to model that regex type in such a way that all the possible combinations of regexes would be represented by it, and they'd only combine them all in certain ways.
That your binary operation on the set of valid regex only produces new valid regex. So like you could not combine them in such a way that they don't produce a valid. Like if you're changing the binary operator rather than the regex itself. If that makes sense.
Yeah, so I think what you're alluding to is a very important distinction. So where I have shown that it goes from an A to an A to an A without dependent types, so even in Haskell, you could define something that is a monoid. It implements the type class. You could define an instance for your type class, but without a property-based test or dependent types or something like that, you really don't. There's no guarantees that it does that. Yeah. So, yeah, good question. So CSS selectors. Does anyone do CSS? Yeah? In anger? Sometimes?
Well, yeah. there's a reason why it's crappy style sheets.
Yeah. So how about CSS selectors? Are they closed? I had to look this up.
You can come up with invalid ones very easily, like it's blue and not blue.
Right, but not as a special syntax. Yeah. So you could model them as closed. If you had button and button primary, you could combine them to your append operation, your append operation, which is your semigroup, could put a space in between them to generate the output CSS or the output class name. Is it associative? Yeah. Yeah, if you were to model this such that you could append these things however you wanted to, I think it's associative. Yeah. Identity? Do we have an identity for them? Yeah, just empty. That works. What do I have there? Idempotent. Is it idempotent? No? Who here thinks it is, and who here thinks it is? Who here thinks it is idempotent? Who thinks it's not? Okay, you all can fight it out. No. So, as it turns out, if you were to provide the same CSS selector on an element twice, it really has no output, no difference in output in the browser. So, in my mind, yes. Is that a little bit wishy-washy? Perhaps. But the net outcome in the browser and the way that the browser is going to treat that and style it, it really doesn't matter how many times you add the same class to it.
Question.
Yeah.
In your implementation, could you make it idempotent?
Oh, for sure.
Just check if it exists and then,
Yeah.
if so, it's not duplicated.
Sure, you could. Yeah. I think for me, the thing that I like is that I know that if this is happening because of the domain that I'm working with, then all of those things are really needed enhancements that I could make to it. But it's not really going to mess up anything that I'm doing to do it simply, or to do it, there's a word I'm wanting to use, trivially. It's also not the word I'm wanting to use. But I could be very naive about my implementation is the word that I'm looking for. And it still is going to be okay, because what I'm dealing with automatically has that. So what about commutative? Is it commutative? Do we remember what commutativity is? Yeah, it's commutative. Doesn't matter. So if we have some element in class name button primary, or button primary button, it really doesn't matter. The browser's still going to render it the same way, given the same style sheet. All right, any questions on those?
So this is a semi-lattice?
Yeah. It's probably a lot more than that, but in this case, yeah, it could be. You could view it as that because it upholds all of those properties. There may be other properties that it upholds that I hadn't even thought about. There probably are, but yeah, very good point. Cool. Any other questions on this? Okay. So, what are our key takeaways from all of this? So we can use abstract algebra in any mainstream programming language that's not Go, basically. It's easy to model the structures. We would need something like property-based testing to validate whether or not these properties are upheld in any language that doesn't have dependent types or is not a theorem prover. But we can still do those, so it becomes easy to use. Also, we can start with whatever domain that we're working with, and then we can ask ourselves, can we write, or is there a value a way that we can uphold the different properties? And the more properties that we can uphold, great. The more theorems that we can prove. That's how abstract algebra got started in the first place, is people were trying to figure out, if I have these properties, what theorems can I prove about them? And the more properties you have, the more theorems that you can create, which I think makes sense. Many more properties and structures of abstract algebra. I basically stayed in the group category, but there's group, there's ring, there's lattice-based. There's a lot of different smaller subsets within this set of abstract algebra that you can deal with. So this I actually got from this is actually Wikipedia. Obviously, you can tell by the amazing color choices that they used. But you can find different things like this. You can search for any of the different structures that you want to, and hopefully that helps you to reason about your code and maybe allows you to model whatever domain you have in a way that will uphold some of these properties, and then you can abstract a lot better about them. Here's some resources that I have that I use to try to come up with some of these slides and to learn more about them. The top one is the link to these slides. The second one, I blog a little bit on Medium about some abstract algebra stuff. And then, yeah, some others. The others are just things that I found really helpful for learning this stuff, or other libraries that already exist that I was able to use for it. With that, thank you all very much. Cool. Question?
So when you said to analyze your domain to see what properties are there, one was to do that, and they saw that their domain lacked properties. Should the response be to know that and embrace that, or should it be to modify your domain to add the properties you're missing?
That you'll have to discuss that with your product owner. No, I mean, it is what it is. Like, if you have, so what I would say is, don't try to force the thing if you don't have to, or it's probably not a great idea to try to force something in. But if these things naturally arise, then take advantage of them. You know, yeah. Any other questions? Okay. Yeah.
Some of the other interesting, so there's group
Yeah.
and ring that I've seen. What are some of the other interesting ones to maybe take a look at?
Yeah. So I mean, you've got so a ring is going to be. So the reason I skipped over ring and went straight to lattice is because lattice kept the binary operation, a single binary operation. As soon as you go to ring is going to have basically a multiplication. So it has to have two binary operations for it. There's another one that I can't come up with that's actually past that. But field. Thank you. I was like, it's right there. Yeah. So there's lots of different ones that you can look up in different properties, and several really good talks. This one right here is by Gabriel Gonzalez, and he actually goes into, it's much more of a Haskell approach, where he takes large, complex, ugly-looking type signatures for different functions and things, and breaks down why it's very easy to reason about all of this, because he's basically just stacking monoids on top of each other. They're different monoids, but they're just stacking on top of each other, and that once he knows that it's just monoids stacked on top of each other, then it's really easy to deal with and reason about.
Oh, that's the YouTube channel one?
That is the YouTube one. Yes, that's correct. Yeah, I was going to tiny URL it, but it felt weird to tiny URL, something that wasn't
we
mine.
have a category :algebras, and that has a whole bunch.
Yep. Yep, and this will lead you to the rest of that if you traverse the wiki tree. Yes?
I found your presentation to be one of the most approachable to somebody who's a relative beginner to these materials.
Thanks.
You plan on posting your slides publicly?
Mhm. Yeah, the very top link.
Very good.
Yep.
Thank you.
Yes. Yeah. So that is there, and I've got most of the. I didn't want to fill it with a whole bunch of code because I didn't want it to be how do you do abstract algebra in TypeScript? Like that was not the intent. The intent I did want to show it in a language that didn't have a whole bunch of advanced type features.
Do you plan on doing a follow-up to add more of the categories, more of the different items, kind of in the same veins for this presentation?
Well, I would love as soon as I learn them. Yeah, as soon as I learn them, this is where I'm posting most of my stuff here is on Medium now. I did have my own it's easier. They manage all the stuff. I don't have to have a VM or all the junk. Yeah. So yeah, I'm definitely adding stuff to there. I don't stick to just strictly abstract algebra. Most of the stuff I do have is TypeScript just because I believe it's a pretty good language that unfortunately has been hijacked by Angular, and there's you can write some cool code in TypeScript that doesn't involve using the class word and mutable stuff everywhere. Yeah. Any other questions? Yeah, sure.
I think you possibly already answered it. But which ones have you actually used in production, or you're oh my gosh, I totally used a lot of semi-lattice. Let me tell you. Do you have any stories like that?
Oh yeah. So the ordering one for sure. In fact, I put the ordering one where you can just compose all the different orderings however you need to. So basically, in this case, an ordering is something that if you have an A and another A that you want to compare, and that goes to either less than, greater than, or equal, then you can combine those together, and then you can also combine the less than, greater than, or equal together. So you've got a monoid for just the less than, greater than, or equal. So if they're equal, then they're equal. But if one's greater than the other one, then you take the first one. So you could compose all of those things together, and I've actually got that in production. I can't say the client's name, but it is in production on a fairly popular food service industry customer. But what that allowed me to do was to be able to take, rather than doing some rather than explicitly doing some sort of, it's all TypeScript, so it's basically JavaScript. So rather than doing sort and then basically having some lambda that takes two values and just having it all implicitly in a lambda, I can encode it into structures that can be composed together in different ways. And so now what I can do is I can say, did you pass me a sort? And if you didn't pass me a sort, then I can have a default sort that is just this value that has been composed by all of these other orderings. And if you didn't, and if you did, then I'll take whatever you've given me. But I have now a default sort, and then you can compose any of these other sorts together.
Is it kind of like sorting one column of data, or sorting complex, multi-column sorting?
You can do any of that you want.
Or whatever, and
Yeah.
it handles all of it.
Yeah.
Oh, that's cool.
Yeah. Because as it turns out with sorting, or the ordering that I have, which I talked about it a little bit with foldMap, where foldMap is kind of gets in the vein of contravariance. Ordering, as it turns out, because we have an A that's going, we have some generic structure that goes to a concrete structure. That's a prime example for using contravariant functors. So what you do is rather than, this is a bit beyond the talk, but it answers your question, because typically with a covariant functor, which is the functor type class in Haskell, what you do is you extend the output of whatever the thing is. With a contravariant, what you do is you say, I can't modify my output because my output has to be greater than, less than, or equal. But what I can do is I can extend the values that I accept as input. I perform that function on it, that mapping function, to get to the value that I already have. So from that standpoint, my sorting algorithms, or my ordering algorithms that I have are for strings and for numbers. But it works on any structure that I want to, because it's also contravariant. So I can extend the first. And actually, I do have a blog post on all of that on that Medium link. Okay, I think we're probably coming up on time. Okay. All right, any other questions, please let me know.